An HTETCO generator is not a readily recognized term within the field of electrical engineering or power generation. The absence of readily available information about an HTETCO generator raises several possibilities. Firstly, it could be a highly specialized piece of equipment used in a niche application, therefore not widely publicized or documented. Secondly, the name itself might be a misnomer or an internal code used by a specific company rather than a universally recognized product designation. Thirdly, it's possible that the term refers to a generator design that is either experimental, obsolete, or even fictional. To explore these possibilities further, let's consider the common types of generators and the principles upon which they operate. A generator, in its most basic form, converts mechanical energy into electrical energy through the principle of electromagnetic induction. This principle, discovered by Michael Faraday, states that a changing magnetic field will induce a voltage in a conductor. This voltage, when connected to a circuit, will cause a current to flow. Most generators, regardless of their specific application, consist of two primary components, a stator and a rotor. The stator is the stationary part of the generator and typically houses the armature windings, which are the coils of wire in which the voltage is induced. The rotor is the rotating part of the generator and contains the field windings, which create the magnetic field. The rotor is driven by an external source of mechanical energy, such as a turbine, engine, or even a hand crank. There are two main types of generators based on how the magnetic field is created. Firstly, synchronous generators, and secondly, asynchronous generators, also known as induction generators. In a synchronous generator, the rotor is magnetized by a direct current DC field winding. The speed of the rotor is synchronized with the frequency of the generated alternating current AC electricity. Synchronous generators are commonly used in large power plants because they can precisely control the output voltage and frequency. In an asynchronous generator, the rotor is not directly magnetized. Instead, it relies on the magnetic field produced by the stator windings. Asynchronous generators are simpler in design and less expensive than synchronous generators, but they are also less efficient and more difficult to control. They are often used in wind turbines and small-scale hydroelectric power plants. Regardless of the type, all generators must adhere to certain fundamental electrical principles. Ohm's law, which states that voltage equals current times resistance, is crucial in understanding the relationship between these three parameters in a generator circuit. Kirchhoff's laws, which govern the flow of current and voltage in electrical circuits, are also essential for analyzing generator performance. Furthermore, generators must be designed and operated in accordance with relevant electrical codes and standards. In the United States, the National Electrical Code, (NEC), provides guidelines for the safe installation and operation of electrical equipment, including generators. These codes cover aspects such as wiring methods, overcurrent protection, and grounding. Article 445 of the NEC specifically addresses generators. It provides requirements for sizing conductors, overcurrent protection, and other safety measures. The NEC also provides tables that are used to determine the appropriate size of conductors for different ampacities. For example, NEC Table 310.16 provides the allowable ampacities of insulated conductors rated up to 600 volts, 90 degrees Celsius, in free air, based on the conductor size and insulation type. This table is essential for ensuring that generator wiring is adequate to carry the expected current without overheating. Overcurrent protection is another critical aspect of generator safety. Circuit breakers and fuses are used to protect generators from damage due to overloads and short circuits. The NEC requires that generators be protected by overcurrent devices that are sized appropriately for the generator's output capacity. Grounding is also essential for generator safety. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to trip overcurrent devices and prevent electrical shock hazards. The NEC requires that generators be grounded in accordance with specific requirements, depending on the type of generator and its application. In addition to the NEC, other standards organizations such as the Institute of Electrical and Electronics Engineers, IEE, develop standards for generator design and performance. These standards cover aspects such as testing procedures, efficiency ratings, and harmonic distortion. IEE Standard 115, for example, provides test procedures for synchronous machines. If an HTETCO generator exists, it would need to conform to these fundamental electrical principles, codes, and standards. Given the lack of readily available information, it's possible that it represents a novel approach to generator design, or perhaps an application-specific adaptation of existing technology. It could also be a term specific to a particular manufacturer or region. To further investigate the possibilities surrounding an HTETCO generator, it's helpful to consider some of the advancements in generator technology that have emerged in recent years. One such advancement is the development of permanent magnet generators, PMGs. PMG use permanent magnets to create the magnetic field, rather than field windings. This eliminates the need for a DC excitation system, which simplifies the generator design and improves its efficiency. PMG are becoming increasingly popular in wind turbines and other renewable energy applications. Another advancement is the development of high-temperature superconducting generators. Superconducting generators use superconducting materials in the windings, which allows them to carry much higher currents than conventional generators. This can lead to smaller, lighter, and more efficient generators. However, superconducting generators are still in the early stages of development and are not yet widely used. Another area of innovation is in the development of more efficient and reliable generator control systems. Modern generator control systems use advanced digital signal processing (DSP) techniques to monitor and control generator performance. These systems can optimize generator efficiency, improve stability, and provide advanced diagnostic capabilities. Therefore, if an HTETCO generator does exist, it could potentially incorporate some of these advanced technologies. However, without more information, it is impossible to say for sure. It is possible that the term refers to a proprietary design or a specific application of existing generator technology. In conclusion, while the term HTETCO generator is not widely recognized, it does not necessarily mean that such a generator does not exist. It could be a specialized piece of equipment, a proprietary name, or even a reference to an experimental design. Further investigation would be needed to determine the true nature of an HTETCO generator and its place in the world of power generation. The basic principles of generator operation, including Faraday's law, Ohm's law, and Kirchhoff's law, still hold true and would apply to any generator, whether it is called an HTETCO generator or something else. Finally, compliance with the NEC and other relevant standards is paramount to safe operation of any generator.